Right, good morning. My name is Will Law from Akamai, and I'm going to be addressing a comparison between our formats. It's rather interesting that 2 years ago, we had really no low latency solution, and now within the last 3 months, we have the luxury of 3. But along with that luxury comes a problem. How do I deploy? Do I choose one of these? Can I deploy all 3 of these concurrently? So a quick note on nomenclature. A number of us have been struggling to name these consistently. I myself started calling Apple's version LL-HLS. Turns out it's easy to write, but it's very difficult to say that. And in corresponding with Roger, he calls it LL-HLS, low latency HLS, and I think we should at least call it what Apple call it. So for this talk, I'm referring to the Apple solution as LL-HLS, and LHLS is going to be the JW community version, and then dash low latency, just so you know where I'm going on the nomenclature side. So, released on June 5th, Apple released something we've been waiting for a long time, which was their implementation and an extension to HLS, LL-HLS. We had, prior to that, April 2018, demoed a lot at FOMS, released at Demuxt, headed by JW, and really representing a class of solutions that both Twitter and Twitch use, which is a chunked-based delivery protocol. It's using HLS as the descriptive format, but combining it with chunk-based transfer. And we also have the dash low latency proposal, which is now available for community review on the website. I put the link up there. We've also, within Dash IF, been working very closely with DVB. So we've harmonized the 2 low latency solutions around Dash. So this is our third contender as we look towards low latency implementations. It's interesting to first look at the commonalities because we tend to focus on the differences. There are in fact a lot. All 3 of these solutions require content to be chunked and coded. And I'm not using the term chunk lightly here. I'm using it in the stricter CMAF definition. A chunk is a MOOF and an MDAT pair. A concatenation of chunks forms a fragment. A concatenation of fragments forms a segment. So chunks are anywhere in the 33 millisecond to 300 millisecond range, whereas segments are 2 seconds, 6 seconds, 10 seconds. All 3 support that. End-to-end latencies, 2 to 10 seconds and up. They're all compatible. Are they backwards compatible with older players? Yes. Are they cacheable by CDNs? Do they use HTTP for deployment? All 3 do. Do they support DRM? Yes. Do they support ad insertion? Yes. Now, in theory, they support ad insertion. Obviously, it's not a lot of working implementations at low latency today, but the definition of the protocol allows it. Do they support multiple codec types? Indeed, they do. Allow ABR playback, and all focus on HTTP delivery. So on the surface, then, they appear remarkably common in both their capabilities and the transport that they use. But now let's look at some of the differences, because that's where it gets interesting. So on this slide, I'm coding a yes as a green and a red as a no. That doesn't necessarily mean green is good. It just means it's yes for the attribute. So they differ primarily in using chunk-encoded transfers. So this is not chunk encoding of the content, but it's the HTTP trunk-encoded transfer to get it out to the client. So that's not used in the Apple solution, but it is used in the other 2. Describing the internal segment structure. Apple does describe the internal segment structure. You know where the chunks are in a segment. You do not know where the chunks are in the other 2 solutions. Do you require a playlist refresh with each chunk? So on the Apple side, you do. It's part of making that description available. The other solutions do not. Object always delivered at line speed. The Apple chunks are delivered at line speed, and therefore you can measure that download. They are not delivered at line speed. They're delivered at the speed at which they're being encoded with the other solutions. Can you separate the server for the playlists in the segment? Because of H2 push requirement on the Apple side, they're both bound to the same edge server, but for the other solutions, they can be decoupled. And I'll go into why that might be a benefit. Require HTTP2 for the last mile for maximum efficiency. Again, a divergence. A smart origin to modify playlists is another requirement. And then deterministic startup. You have a lot more visibility in the Apple solution when you're starting the stream than you do in the LHLS and in the Dash. So there are some differences, and I'm just going to explore some of these in a little more depth as we go forward in this presentation. So let's focus on one of the biggest differences, chunk transfer encoding. So LHLS and Dash use chunk transfer encoding to release the segment. So the encoder is making the first frame, maybe the first 33 milliseconds of data. As it makes it, it posts it out to the CDN, and the CDN receives that, continues the post, and pushes it all the way to the client. So the benefit is you only have to make one request. If your segments are 6 seconds long and there's 180 chunks in that segment, you make one request, you receive all the chunks in a linear sequence. And it allows very small chunks to be used. Most of the chunks we use in practice are, in fact, one frame, 33 milliseconds in duration. The problem is that they are produced at the rate that the encoder is making them. And if you have a 6-second segment, you'll notice that no matter how much end bandwidth you have between your client and your server, you'll always get the segment in 6 seconds because it's limited by the speed of the encoder and not the line speed at delivery time. So here's a little animation to illustrate that. So again, with the chunked encoded, you make a request for the complete segment, and the segments are released at the rate they're being produced. It's a slightly artificial diagram there. I should have produced the segment slowly and then delivered it quickly, but you get the idea. With a non-chunked encoded solution, in other words, the Apple approach, you have to physically request every chunk. So it's going to be a request for a chunk, which Apple calls a part, and then a quick delivery of that part. And that request sequence, there will be 4 requests if there are 4 parts in that segment. And they happen a lot quicker than I'm showing here. Now, I don't know if you appreciated the data Ali just presented. I'm stealing some of his slides here. That's pretty seminal research when it comes to overcoming the problem I just mentioned with chunk transferred content. Bandwidth estimation has been the problem. There's been some grand challenges issued for ICME around that exact issue. So the elegance of this solution, which says that your chunks are not all the same. Some are together and they're useful for bandwidth measurements, some are not. And with JavaScript, we can separate the two and actually make accurate bandwidth measurements. This is a fundamental advance for low latency streaming, and I think one that's really going to help the solutions that use chunk-based transfer to do accurate ABR. If you look at a lot of the demos you see, they're all doing single bitrate, so they conveniently avoid the problem of bandwidth estimation, which is a prerequisite to being able to implement your ABR scheme. So this solution is fresh. It's come out in the last couple of months, and it's changing the landscape a little bit regarding chunked encoding. Don't know if you saw that figure when he brought up the slide. That was a 96% accuracy in estimating the actual bandwidth. That's pretty good. So why not use chunked encoding transfer? So at its optimum, an Apple HLS player is going to request chunks the moment they are produced. It'll get the manifest quickly. It will request the chunk. It also needs to request them in the order that the encoder is making them, because that's the decode order that it has to give to its decoder. So it's not going to request them out of order. What's interesting is that chunk transfer encoding gives you this for free. The player makes one request for the segment. It's given the chunks in the correct order, and they're released to the client as soon as they're released to the encoder. So I scratch my head about this, and especially with the advances in bandwidth estimation, it might be the case that the reason Apple are avoiding chunk transfer encoding is maybe around intellectual property reasons. Maybe Apple are concerned that other solutions use this and therefore they're not comfortable using it. Because I think Apple thought through their solution very carefully. They're keenly aware of what chunk transfer can bring or not. And this might be, I'm happy to stand corrected on this, but this might be one of the reasons for not using chunk transfer encoding in that solution. Now, what Apple does have is internal segment durations. Why is this useful? It's useful because the player can understand where the IDRs are at any time. With a Dash or a LHLS solution, the segment is an opaque box. A Dash, we know that there's an IDR at the start, but for a 6-second segment with 3 2-second GOPs, you don't actually know where those intermediate GOPs are. And there are points that you could, in fact, start decoding the segment. So knowing where the IDRs are improves your startup logic. It also allows you to switch at intermediate points, not only at the start of segments. So you could switch every 2 seconds instead of every 6 seconds. That's very useful if you've only got a 3-second player buffer. So what is the point of describing non-independent chunks? If you understand the Apple spec, they describe chunks that are independent, meaning you can decode forward from these points. They also describe chunks that are non-independent, and you must They're just successive chunks and they depend upon a prior chunk. The reason is to allow latency that's less than the IDR spacing. And this is also useful for startup. And remember, you're subject to the Apple doctrine that you must deliver the part at line speed so its bandwidth can be reliably measured. So I can show an example of this here. On the left, we have a LL-HLS example media playlist. And say I'm a client and I'm asked to start playing the stream. It's my starting buffer that determines where I'm going to start. So the player builder says I must start with a 1 second or a 2 second or a 3 second buffer before I get going. So let's say the smallest start I could have here is the closest independent part, which in this case would give me 1.3 seconds of buffer. But if I only wanted 1 second of buffer, I could load that first independent part and then just 2 of the other non-independent parts, and off I go, I start my playback. So I have some flexibility because I have visibility into the segment. Now, say I wanted a 2 second buffer. Well, I can read up in that playlist and again figure out that the previously described independent part would give me 2.1 seconds of buffer. And I could start there. So I have the ability to choose my starting point. Now, if we look at low latency HLS, imagine it didn't describe the intermediate parts and it was opaque to the internal description. Well, now my choices are basically quantized around my segment duration. There's the segment that I happen to drop into, which in this case is 2.7 seconds behind live, or I would have to go all the way back to the prior one, 4 seconds away, which would be 6.7 seconds, and those would be my two solutions. So the internal descriptions are quite useful at startup for getting an accurate starting buffer. So that's useful. Now the question is, well, how do the other formats deal with this problem? So how does LHLS? So imagine you're a player now, you're presented with this manifest, you need to start. Well, you're going to load the last segment. And because these are 2 second segments, you're going to have a random amount of data, somewhere between 0 and 2 seconds in your buffer. So if you're lucky, if you want a 1 second starting buffer, you may be able to start immediately, or you may have to wait some period of wall clock time and get the additional data before you can start. And you only know this after you've downloaded the segment. Now you can know this very quickly, but you may have to wait for more data when you start. Now say you know you need more than 2 seconds of data. Well, in that case, you would go and download the prior segment. You know it's got 2 seconds. But again, you're quantized around blocks of 2 seconds, or maybe this arbitrary last segment. So there's work the players have to do in the alternate solutions in order to start and to minimize the delay at startup time. LL-HLS also introduces a new topic, which is media playlist variability, because it introduced the ability to have query args to modify the playlist. So if we look at older Apple before V9 or else an LHLS implementation, you essentially have one media playlist. So there's our 800 kilobits per second video playlist. As we shift to the new low latency solution, there's a lot more options. So here I show it. Clients requesting push, clients requesting media sequence number 273, but then differing in whether they're requesting a report or requesting skip function, which is entirely rational. So if you go with 18 parts per segment, which is 333 millisecond part in a 6 second segment, and you have a mixture of clients that push and those that don't, and clients that skip and those that don't, you're going to have 72 versions of that media playlist at your CDN edge. So that's a lot more than one. Now, there's a usefulness, as I just described. These are all bringing useful characteristics, but as a CDN, we have to ensure that we're delivering the right one of those 72 and that it's fresh at the edge, and that's a complexity problem for us. Also, the request rate is quite different, and I'm trying to make an animation to illustrate this here. So let's take the example of a 6 second segment with 333 millisecond chunks or parts, depending on your nomenclature. So the dash approach doesn't require a text file or manifest update with each segment. So it looks like this. It's basically the 6 second segment is requested once every 6 seconds, and the segment takes 6 seconds to be delivered by the encoder. So we get a cadence. There's an audio request and a video request, and we're going to get 20 requests per minute per client because of that. 2 times 10 for 6 seconds. If we look at how LHLS can do this, It's essentially the same, but it's adding in the media playlist request once every 6 seconds because there's no part description. So it's looking very similar to the dash low latency. And in fact, you can use common audio and video segments between the two as long as you're using CMAF segments in both cases. This gives you 40 requests per minute. We got the same audio and video request for the media segment and then the additional media playlist requests. If we look at LL-HLS, it ends up looking like this. In fact, PowerPoint can't animate it fast enough. There should be 12 requests per second, adding up to 720 requests per minute. Because you're getting a part that's being requested every 333 milliseconds for audio, for video, and then also a media playlist update to describe both of those. Now, in deference to the client, half of these requests of the client should be fulfilled by the H2 push. So the client should be seeing 360 requests per second crossing the wire, but the edge server is going to see the full 720 requests per minute. So there's a large variation. Now, all that requesting is giving you some benefits with the LL-HLS approach. It's describing the internal segment, it's delivering it at line speed, but it's coming at a cost, and we can quite clearly see the request cost. Every request on a server at some point costs something. Might cost a very little bit, but when you add up 1 million people all requesting at that rate, it gets high quite quickly. Also, there's been some confusion with how H2 push works with LHLS. It's actually relatively simple. I'll quickly go through. The client makes a request for a playlist, and it says, hey, Mr. Origin, I'll allow you to push me something. So the Origin responds, and it adds a preload link header, a response header, giving the path to the last part that's described in that segment. But notice that's not an H2 response there. It's the CDN response going back to the client. It returns the playlist, then it has to go back to the Origin, fetch that last part, and as it receives it, it then adds it as a push on the same response that's returning the playlist. So when the client turns around, reads the playlist, and requests that part, it's already been pushed to it. So notice that the H2 push is only required at the CDN edge. It's not a chained series of H2 pushes that's coming from the Origin all the way through. The time it's saving is those 2 round trips. Otherwise, the client would go back to the CDN, CDN, back to the Origin, and all the way back to fetch it. But it means that the edge server needs to deliver both the playlist and the segment. And this is a problem because in server-side ad injection, those two are decoupled. Your ad provider is manipulating your manifests, and your CDN is delivering your segments. So with this approach, we have to push those two together. The segments are a lot heavier, so ad providers today, ad decisioning systems are not used to delivering media segments. They're purely dealing with small text files. So we have additional work there. So there are some significant changes that challenge us in order to deploy the new Apple solution. One is the Origin intelligence. So if you're building an Origin, you have to be much smarter about mutating the playlists that are coming out. There's not one version, there's many depending on the query args. And we as a CDN need to cache them and ensure that they're fresh. There's that large increase in request rate per client. The relatively significant increase, or the inability to decouple manifest delivery from segment delivery, and the requirement for H2 push. So while Akamai today supports H2 push for our web properties, we don't actually support it for our media properties. We have a project to get this underway, but we don't have an announced date for it yet. It's not something we do support. And this is pretty true for most large CDNs. I do think Fastly support it today. I'll give them credit for that. So just some rapid conclusions, and these are just mine. I think a large part of the design of LL-HLS might, in fact, be driven by IP considerations. And that's important. It's also unfortunate for engineers. I want us to deliver the best solution all the time with the best pieces, and it's disconcerting when IP comes in there. It is possible to deliver an interoperable working solution between the dash and the LHLS implementations. They can use the exact same media segments, the exact same origin, and in fact, it's very cache efficient. So that part is working. However, you need to write a custom app if you go to Apple ecosystem devices, because the native Player AV Foundation is not going to play that. It's going to want LL-HLS for its low latency. And I think this issue of not being able to decouple the segments and manifest is going to have a big impact on deployment, because it's for anybody looking at server-side ad injection. And just always a reminder, as Tim showed at the beginning, if you don't need low latency, it's really simple just to use contiguous 2-second segments. You can get broadcast equivalents in the US. It won't quite give you that in Europe, but it sure gives you a lot less complexity and a lot less headache at the end of the day. And we'll deal with questions at the end. Thank you.